Okay, so in the second video, we are going to talk about Hermitian matrices and eigenvectors and eigenvalues. So let's see, what's a Hermitian matrix? A matrix is Hermitian. So A is Hermitian if and only if A is equal to A conjugate transpose. Okay, so in particular it has to be a square matrix. And so for example, this is a 2 by 2 Hermitian matrix. So the entries on the diagonal have to be real. So it could be like this. And then the matrix has to be equal to its, if you conjugate the entries, then and you transpose the matrix, you have got to get back to the same place. So for example, if this was 1 plus I, then this entry must be its conjugate transpose, so it must be 1 minus I. Okay. So if A is Hermitian and real, then it's also a symmetric matrix. Okay, so now we say that a vector phi is an eigenvector of A if A times phi is lambda times phi. So what A does to phi is it just shrinks or stretches it. Okay, in general, of course, lambda is going to be a complex number. Okay, so now there's this beautiful theorem about Hermitian matrices, which is called the spectral theorem. So what the spectral theorem says is that if A is Hermitian, implies that A has an orthonormal set of eigenvectors with real eigenvalues. Okay, so let's call these eigenvectors phi sub 0 through phi sub k minus 1, and the corresponding eigenvalues, let's call them lambda naught through lambda k minus 1. And so what this is telling us, okay, so let's pretend for a moment that A was a real matrix. So it's just a symmetric matrix with all real entries. So then what is the spectral theorem telling us? Well, what it's telling us is, if you look at the unit ball in this k-dimensional space, so I'm thinking of k as 2 right now, you can think of anything, then what happens to it under the action of A? Well, to figure this out, what you have to do is you first have to locate the eigenvectors of A. And perhaps one of the eigenvectors is this one, and one of them is that one. So let's say these are the two eigenvectors. They are orthogonal to each other. And now what we are guaranteed is that what A does to this is it just scales each of these. Okay, so what it might do is it might shrink this vector, and it might expand this one. Okay, so, and of course, once we know what it does to each of these, we know what it does to any linear combination. And so what it does is it takes this circle or a sphere in k dimensions, and it converts it, sorry about my drawing here, it sort of distorts it into an ellipse like this. Okay, so A maps the sphere, the unit sphere. Okay, so in this case a circle into an ellipse and the unit sphere into an ellipsoid. Okay, where there are k principal axes, whose lengths are given by these eigenvalues, and then you have this kind of object, except maybe in 3 space or 4 space or whatever you have. So let's look at an example of this. So for example, we had already looked at this operator x, which was a bit flip operator. It was given by this matrix, which is of course Hermitian. And so we can ask, what are its eigenvalues and what are the eigenvectors? So this you can solve just by inspection. You can it's sort of easy to see that one of the eigenvectors of x is plus. So the eigenvectors of x are plus and minus. Okay. So what does x do to plus? Well, what is let's write it out in the usual vector notation. So what's plus? It's 1 over square root 2, 1 over square root 2. And what's this product? It's exactly 1 over square root 2, 1 over square root 2. Right? So what's the corresponding lambda? What's lambda sub plus? Well, it's exactly 1. Okay, so lambda x maps plus to plus. What does x map minus to? Well, it's exactly the same thing, 1 over square root 2 minus 1 over square root 2. And this time it flips them, which is minus of what we started from. So lambda minus is minus 1. Okay, so x has 2 eigenvectors, plus and minus, with eigenvalues 1 and minus 1. Okay, but you could also ask, well, how would you figure out these eigenvalues and eigenvectors if you couldn't guess them? Well, then, just to remind you how one does that, you sort of solve. What you say is, for example, let's say you wanted to work this out instead for the Hadamard transform H, which is 1 over square root 2, 1 over square root 2, 1 over square root 2, minus 1 over square root 2. Well, again, actually it's a little easier to guess what the eigenvectors and eigenvalues are, because remember what the Hadamard transform does? There's the 0 state, there's plus, there's minus, there's 1. And what the Hadamard transform does, it's a rotation by pi about this axis here, right? About this pi by 8 axis. So what are the eigenvectors going to be? Well, clearly one of them should be this vector, the pi by 8 vector, and the other should be orthogonal to it, right? This would have eigenvalue 1, and this would have eigenvalue minus 1, because it flips when you apply h to it. Okay, but let's go back and think about how would you actually work this out. Well, let's carry out, so what you would do is you would say, okay, so I want to find some vector psi such that h times psi is lambda times psi, which means that h minus lambda times the identity times psi equal to 0. But we want a non-zero solution to this, so for this to happen, this must be a singular matrix, so it must have determinant equal to 0. So let's write out this condition. So what's h minus lambda I? Well, h is 1 over square root 2 minus 1 over square root 2, 1 over square root 2, 1 over square root 2. And now we want to subtract off lambda times the identity, so we subtract off lambda from the diagonal. And now we want the determinant of this to be equal to 0, but what's the determinant? It's this times this minus this times this, so it's 1 over square root 2 minus lambda times minus 1 over square root 2 minus lambda minus 1 over square root 2 times 1 over square root 2, which is minus a half plus lambda squared minus a half equal to 0, which means lambda squared equal to 1, so lambda equal to plus or minus 1 as we wanted. And now we just choose each of these values and we figure out what phi must be. Okay, so finally let's let's do one last thing, which is what we said is A has an orthonormal set of eigenvectors phi naught through phi k minus 1 with real eigenvalues lambda naught through lambda k minus 1. Okay, what another way you can say this is that if you were to change your basis to this phi naught through phi k minus 1, then what's the action of A? Well, it's just a diagonal matrix. So in the phi naught through phi k minus 1 basis, so if you were to write A in this phi naught through phi k minus 1 basis, then A would look like this. It would look like lambda naught, lambda 1 through lambda k minus 1. It would be a diagonal matrix because all it does is it takes phi naught. What does A do to it? It multiplies it by lambda naught and so on. So let's call this diagonal matrix capital lambda. Okay. So now we can write A as the following. So if we first do a change of basis, so if we first perform some unitary transformation, some rotation that rotates our standard basis into this basis of eigenvectors, then the action of A is just given by this diagonal matrix lambda. And then if you want to switch back to the standard basis, then we'd be applying the inverse of U, which is U dagger. So what we are saying is A can always be written as U dagger lambda U, where U is a matrix which changes the standard basis to the phi basis, the basis of eigenvectors. Okay, so what does U look like? Well, U, obviously the columns of U are going to look like the phi I, the phi j's. So the first column will look like phi naught, the second column will look like phi 1, etc. The last column will look like phi k minus 1. Okay, and now if you look at it, what does this tell you? Well, A is just the following. It's just lambda naught times the projection onto phi naught plus lambda 1 times the projection onto phi 1 plus lambda k minus 1 times the projection onto phi k minus 1. So you can either read it off of this, right? Because the rows of U dagger are the phi j's, complex conjugated. And so when you multiply all this out, since these phi's are orthonormal, all you will get is the jth row with the jth column, of course multiplied by lambda j, and that's what these are. Or you could just check that when you multiply this times phi times any phi j, you get lambda j times phi j. Okay, so finally what this is telling us is that A can just be written as the sum of lambda sum over j going from 0 to k minus 1 of lambda sub j times the projection onto phi sub j. Let's call that projection matrix P sub j, where P sub j is phi sub j bra phi sub j, sorry, ket phi sub j bra phi sub j.